Okay, so after understanding the ultrasound wave equation, right, we reduced 3 dimension to essentially a 1D propagation, and in that we talked about interaction of this wave with the material medium, right. Namely, the important interactions that we captured were reflection coefficient, transmission coefficient, angle of incidence, angle of reflection, right. So that was one thing, and then that was a specular reflection, and then what we called as diffuse reflection or scattering, and we ended up having a signal model for the scattered signal. So in our case, it is the pressure wave that is reflected from a point which has a reflection coefficient. So this is the part where we identified somewhere what is the physical meaning of the signals that you are going to record and see in ultrasound image. It is going to be related to this reflectivity. How is this 3D distribution of reflectivity to ultrasound, right? That is what we are going to capture. So before we proceed further on the instrumentation and image equation, there is one another interaction that is important that we understand. So far what we have done is we have defined the wave propagation, and then how does this wave interact, more specifically when it encounters an interface, right, where there is two different mediums on either side, right. When a wave encounters that, what happens to it? That's what we have seen so far. Now we'll stretch a little bit beyond and ask ourselves, okay, what happens, right, if this interface or this acoustic scatterer that we modeled, if that is not stationary? So the wave is coming, so the wave is moving, it's traveling, but then it is encountering an interface or a point object which is not stationary, which is moving, right. Then what happens? Okay, so that is important. As you can see in biomedical context, right, where could the motions come from? Well, you could have the whole specular, the surface of your lungs, for example, right, can go up and move in and move out. So to some extent that is possible, but more importantly, what is moving fast? Our blood, right. So it will be interesting to understand what happens when you have a wave that is going to hit some interfaces. It can be smooth interface, or it can be scattering that can come back because of the size is much smaller than the lambda. What happens to it, right? So in this context is where the concept of Doppler ultrasound is exploited. So what does Doppler principle say? This you might be knowing from your high school, right? You would have been told what happens when a train or an ambulance, which is siren, right, when it is approaching you, what do you hear, right? And when it is going past you, what you hear, what you perceive, right? Beyond just the loudness that is getting increased as it approaches, right, there is this frequency, there is a shrillness that will also happen. So if the vehicle, the sound source, right, the siren is on top of a vehicle, so the vehicle is moving, you are a stationary observer, so there is a relative motion between the observer and the source. Okay, in such a case you would have been introduced this concept of Doppler principle, which says, oh, when you do that, your the frequency shift, right. So there is a pitch that is different, what you hear, the shrillness is different. So the change in frequency is proportional to the velocity, the relative velocity. This is what you would have uh, vaguely remember from your high school. Typical examples of a train which is blowing horn, or a siren in an ambulance, where there is a relative motion between the source and the observer, is something that you would have been familiar with. So the same principle when applied to ultrasound signal, not sound signal, that right, the examples that we gave, when it is done to ultrasound signal, which is not a big deal, only the frequency range is different, right, then that is what is called, that aspect is called Doppler ultrasound, which is exploited mostly for moving objects. What is moving objects? Mostly it is blood. Okay, So waves reflected from moving scatterers are shifted in frequency, and the more important thing is that frequency is proportional, the amount is proportional to the velocity of the scattering object. So in simple idea, if I can engineer, I can send a sound wave with certain frequency, right? I send an ultrasound wave with a certain frequency. If I can receive an ultrasound wave that is getting reflected from an object, right, and that object is moving with a velocity, so I can have some ways and means to know what is my receive frequency, I can know what is my transmitted frequency. So the difference between them is proportional to the velocity, right? So if I can measure this, then somehow I can get an idea of an object that is moving with a velocity v. Okay, this is cool, right? I can sit outside, send a frequency in, receive a frequency, analyze the frequency and tell that something is moving with certain velocity. In our case, it is going to be blood mostly, right? So it is very cool, neat principle that is exploited here. So what we will do is, we'll take a very rudimentary approach, just at a very two-step process, right? We will just try to understand what this proportionality constant is, right? It is proportional. So we'll have to set up our problem and quickly recognize what the proportionality constant is. Okay. So let's take a situation. This is very similar to what we started before, right? When wave interaction with the medium. So you have a plane wave that is traveling, right? A plane wave is traveling. Only thing is, instead of an interface that was stationary, I have replaced that with some object which is moving. So in other words, you have a boundary that is moving. Okay. So that is the only difference. Otherwise, you see that these are the plane wave fronts. When it is coming, the other one is the plane wave front that is coming back. So you're going to have reflection, right? And so you have an angle of incidence, you have an angle of reception, right? Incident, angle of reflection, and then you have your wavelength of the incoming, right, the source, and there is a wavelength with which these waves are going after getting reflected. What is new here is this Fm. What is this Fm? Oh, this Fm is again another frequency which you call as the intermediate frequency. Essentially now the object is not stationary, the interface is not stationary. So if I sit on the interface, right, on this object, what is the frequency that I will see of the wave fronts that are coming? Okay, so this is my frequency as observed from the object, and it has a velocity v. In this case, I have put the velocity to be going in this direction to the right. Okay, so given this proposition, what do we know already? What do we want to do? Well, we know the big theme. The big theme is somewhere we will have to find out what is this Fr minus Fi. So the easiest way is start writing it out right from the fundamentals. So the idea would be, we need to relate, you are sending a frequency, you are receiving a frequency. These both are related to this Fm, right, this object that is there, the frequency that is observed when you sit on this, and there is a motion of this object. So what we will do is, we will start with the two-step process. First we will see what happens from the source to the scatterer. So in that sense, if I sit on the object here, what is the velocity with which, what is this? Oh, these are plane wave fronts, right? Different phase, right? High rarefaction or compression, right? High pressure, low pressure is oscillating. So what this line indicates is isoplane, right? What some pressure. So typically you can consider that as a peak pressure, right? Peak positive or negative. So this is the distance between them, is one cycle is your lambda. So in some sense, what is the velocity with which this phase is hitting this interface? Oh, ideally it would be just the c, right, the phase velocity in the medium, but now this object is also moving with a v. So there is going to be a effective velocity, right, because of the relative movement, right. There is going to be an effective velocity of the incoming waves. Okay, so that will be c in effective is c, which is your without any relative motion, minus the component of v cos phi, correct. Yeah, you are moving in this paradigm, you are moving this direction, the waves are arriving, right. So you are moving away while the waves are reaching. So in some sense it is slowing down, at least you will feel that it is coming slower, right. So that is your c effective in. Okay, so this is my c in effective. What do I know? Okay, c in is one idea, but then what is the relationship between c, lambda and then f? This is what we are going to exploit. So what would be your frequency in the medium, right, your intermediate frequency, the frequency with which this is observing, the phase fronts are hitting, right. So frequency will be c by lambda. In this case it is c in effective by lambda I, incoming waves. So lambda is in the medium this side of the incoming wave. C in effective is the velocity, the effective velocity as seen by the observer. So the frequency, the intermediate frequency observed by the moving observer is going to be c in by lambda. F is equal to, right, c is equal to f lambda, if you remember that. Okay, so c in effective is your c minus v cos phi. Okay, so you have your frequency intermediate. This much is fine. Of course, there is one more item here, lambda I. What is lambda I? Oh, lambda I know from, it is in the medium, nothing to do with this guy. This is what I am sending and it is in the medium. So lambda I is related to your c and fi, right. So lambda I is c by fi, that is in the medium. You are transmitting in the medium, straightforward, lambda is equal to c by f. Okay, so I will just substitute this back so that I get my fm in terms of fi, right. Of course, with this factor, fm is equal to fi times 1 minus v cos phi I by c. Okay, so this is one equation. This is based on source coming to the observer, right, of the object that is moving. So now what is the other path? Oh, the other path is after it comes, hits here, there is a wave that is reflected and going back, right, this direction. So now we could do similar argument and understand what will be the effective velocity of the waves that are going out. Okay, what could be the, your fm cannot change, right, you are catching, you are sending out, right, reflecting. So your fm cannot change, but your c out effective can change. Of course, there is a lambda that we need to check. Okay, so we will now take the other path where you are starting with the scatterer and going towards the receiver. What is the effective velocity, the wave that is going out of this observer, right? In the incoming path, we were sitting and observing the phase velocity, the phase that is coming and hitting you. What is the velocity while you are moving? So now while you are moving, it is reflected and sending out back. Okay, so your c out effective is c plus v cos phi r. So c out you have, okay, good. Then, oh, we could also write our frequency m, right. So what we will do is, we will recognize c out, we know what is lambda r. Lambda r is the wave that you are sending out, the velocity with which you are sending out, because the reflected wave is going at certain velocity, which is relative velocity because this is moving. Otherwise, it is the same medium. But now the difference is it's a reflected wave is having an effective velocity based on the interface that is also moving. That is why this is C out effective by Fm. Okay, so this is the lambda r. So if I substitute for my C out effective, I can get C plus V cos phi r by Fm. So what can we do? Oh, I have a Fm here. I had a Fm when I did source to one path. Fm is supposed to be same, right? So I can quickly move around. So your Fr is equal to C by lambda r, right? Fr is C by lambda r, but then I can substitute for my lambda r, right? If I substitute for my lambda r, and then here there is a C, right? There is a C here. So you can make that 1 plus V cos phi r by C. This becomes your second equation. So you notice that from here you can have Fm is equal to Fr times 1 plus V cos phi r by C. So from equation 1 and equation 2 if you combine, right, because you have Fm in both, so you can eliminate Fm and relate Fi and Fr. So Fr is equal to, which is our objective, right? In fact, this is not our objective. Objective is we have to get to Fi minus Fr, but at least we are now in terms of Fi and Fr. This intermediate frequency is gone. So Fr is equal to Fi times this guy. So quickly what we need to do is, this is good, but then you have 1 minus by 1 plus a fraction. What is this fraction? Oh, you have some V cos, so velocity component of this moving object, moving interface with the C. C is your velocity of, phase velocity is your velocity with which the speed is sound is moving. So for most cases you will realize that V is much smaller than your C. C is what? In tissue it is about 1540 meters per second. So if you contextualize, in human body, blood, even in aorta where you have you are talking about 30-40 centimeters per second. So V is much smaller than C. What that helps us do is, you have this 1 minus a fraction by 1 plus a fraction. We can try to make use of this fact that V is much smaller than C, and therefore we can retain only the first order terms. So we can write Fr is equal to Fi times 1 minus V cos phi I by C minus V cos phi R by C. Okay. So quickly from here you can see that we are slowly getting to where we want. What we want? Fr minus Fi. Fr minus Fi is your Doppler shifted frequency. Doppler shifted frequency is Fr minus Fi is going to be this V cos, right? V by C cos of phi I plus cos of phi R times Fi. Okay, very interesting situation. Okay, so now what we will do is, we will pretend, oh, phi I equal to phi R. Okay, if that is the case, let them be equal to some theta, for example, right? Phi I equal to, approximately equal to phi R equal to theta. If you do that, you get this equation. What is this saying? This is saying the Doppler shifted proportional to V. That is what we started out, right? Oh, here you see Fr minus Fi is your Fd, is proportional to V. Of course, you have few other terms here. So you have your cos theta, because it depends on the angle relative orientations, and your speed of sound C. More interestingly, it is also dependent on Fi. Okay, what that tells you is, if I want to increase the shifted frequency, the Doppler frequency, Doppler shifted frequency, I can also increase my Fi. Okay, so this itself is not a big deal. So I can increase my Doppler shifted frequency if I increase my Fi. So shift is proportional to Fi. So higher the Fi, larger is the Fd. But notice, however, that this part, right, this part is not dependent on the frequencies. It depends on only on the velocity and the speed of sound. So in some sense, the percentage change is independent of your Fi. Okay. So the percentage change is independent of your Fi. So of course you see a negative sign here, right. So it depends. So it depends on the frequency. The direction of V is changed. If the so here what we started is velocity is in this direction. What happens if the velocity is, if the interface is moving towards the source, right. So this negative sign or positive sign depends on whether the object or the scatterer is moving towards the source or away from the source, right. So typically you will notice that it will be color coded, right. So when blood in biomedical ultrasound, when you have Doppler to visualize blood flow, then if it is a red color blood flow which is positive, that means the blood is flowing towards the transducer. When you get a negative velocity, that means it is moving away from the transducer, that will be coded in blue. Okay. So that is just a sign convention. Okay. It's from a simple physics point of view, this is what is Doppler principle. But then when we actually exploit this for imaging, there are bunch of trade-offs that are involved, because the whole idea is you want to estimate the velocity, you want to preferably place the blood inside the vessel and register it against the structural image, right, of the organ. So where is that vessel? Inside the vessel something is flowing. So typically you have to do the imaging ultrasound. So what we will see subsequently, you have seen the gray image, gray scale image, right, of the baby sucking, right, in the first slide we showed. So typical ultrasound image, on top of it you will show where the velocity is happening. So in some sense it is little more complicated from an instrumentation point of view, because this is an add-on to the structural image. So we will leave the physics right now, we will jump on to the instrumentation. So with this we will complete the physics of ultrasound, in fact slightly different from the textbook approach, where the subsequent topic of beam forming, beam pattern is discussed in the text. I would like to treat it slightly differently, leave it here, leave the physics here, jump to instrumentation, and in the context of instrumentation we will talk about the signal, right, the beam pattern that is covered. So we will quickly move on to the instrumentation aspect of ultrasound. So a schematic of ultrasound system is as shown here. What is important to notice is there are several different blocks, okay, in the spirit of keeping this to an introductory level, right. In all of these pieces, each of the block there are intricacies, and then how you combine them is going to dictate the various trade-offs that are involved. For simplicity, we will kind of tick on only on the major components here. So there is this transducer. So the idea is you have to generate an ultrasound wave, send it, and then perhaps receive. So the source and the detector, right, similar thing, X-ray tube and the detector. So like that, this is a major guy. So transducer, as we will see, is an important aspect, because it is generating the sound waves and also receiving the sound waves, ultrasound waves. After that, it's all about converting it into some sequencing. Again, we will talk about beamformer as well to some extent. What we will not talk about is all the scan conversion, ADC, post processing, display, all this we will go little light. Okay, this is an important aspect here. This along with beamformer This part is a very important aspect which connects your physics and what you are going to get in the image, the quality of image and the image itself, the different types of image that you can get. So, we will try to give a very bird's eye view on this big picture, but focus little bit more on the major components. Okay. So, with that we will start with the transducers. So, the idea is, okay, I want to generate the sound waves, send it into the body and receive the sound waves. Okay. So, transducer is something that just converts energy from one form to other, right. But in our case, what do we want? I want to send pressure waves into the body. Okay. So, one of the signal is the pressure waves, and then the pressure wave gets reflected, bounced back, as we saw, comes back, and then you are recording it or you are detecting it with another, so you are recording it with the receiver, right, you are receiving it. So, again this is a pressure wave that is coming in hit, but as you know, we would like to take the data and process it and display the image. So, we want to get into the electrical side of it. Okay. So, because then it is easy to handle the circuits, read the signals, display it, amplify, do whatever you want, right. So, the idea here is the signal that is interacting in the body is mechanical pressure wave. However, the signal that you are going to handle and process is going to be electrical. So, this transducer essentially does this conversion. On one side you supply voltage, it generates pressure wave. On the other side, when the pressure wave hits, you want to convert it to the electrical quantity. Okay. So, typically this is a scanner look alike, and you will notice bunch of different transducers depending on the imaging study, right. If they want to take a abdomen scan, for example, right, you want to have the properties of being able to reach deep. That is more important, because usually, you know, abdomen region is it's bulkier, where you can also have some transrectal, right. So, you can go through orifice and you can see inside, or you have some, here what you see is a linear array, right. So, maybe shallow organs, say breast imaging or MSK, right, just muscle. If you want to do that, then depth is not that much compared to your abdomen that you want to do. So, you have different size and shape of these transducers. All of this are designed based on the physics of how you are able to generate the wave, how does the wave interact with the medium, and how you are able to receive and say what you got from where. Okay. So, these are not just for aesthetics or convenience, these are all designed such that you are able to get appreciable signal quality from different regions of interest. Okay. So, the transducer has several components. Major active component of interest is your piezoelectric material here. What does that do? The piezoelectric material generates ultrasound and also, right, generate and detect ultrasound. So, the advantage here is this material can act both as generating the ultrasound, so it can be used in transmit and also receiving. Okay. So, that is the idea about this piezoelectric crystal, which is why it is very powerful. So, you could have the same crystal act as both transmit and receive. Okay. So, when you have voltage, it provides vibration and it provides ultrasound waves, right. So, you supply electrical voltage to this crystal, it starts to vibrate and you create a pressure wave. In the reverse, when you have a pressure wave that is hitting, it will create a voltage. Okay. So, this is very important. Lot of material property, material science goes towards engineering this. Of course, our spirit here is to just understand, okay, this transducer is able to generate an ultrasound wave and receive an ultrasound wave, or it converts pressure wave to electrical quantity to pressure wave. Okay, how it is material is engineered to do that is not part of this introductory level. So at the first level we talked about size and shape just to give a feeling for that. So the thickness of the material, right. So we want material and we are interested in only one kind of wave. What is that? Compressional wave. So we want the material to do only this, so that the pressure wave is compressional, plane waves that we talked about, right. So compressional waves is what we want. And so depending on the frequency of interest, right, thicker material will usually give you a lower frequency, thinner material will give a higher frequency. So you notice when you go higher frequency, if you want to generate higher frequency waves, then the material becomes thin, the crystal becomes thin, and therefore from a materials point of view it becomes challenging because it is thin, right. So it will be brittle, it can break, so you have to and then you have to make sure that it has to be cut to size, different shapes that we want. So all that becomes complicated. Okay, so the higher the frequency, the manufacturing of these crystals becomes little tricky. Okay. But we know something. What is this frequency related to? Oh, frequency relates your lambda, right? Some C and then lambda, and we already passingly mentioned this lambda is an important parameter, right? You want the wavelength is related to resolution. So higher the frequency, lower will be the lambda, and so better will be the resolution. But then you notice the challenge also is coming. So we'll just identify that and leave it at that, because we are not going to go into the depth of how to engineer this material. So you have several different materials available. By far PZT, right, is one that is used. You have PVDF, polyvinylene difluorine, but then that is a very sensitive material, and so usually what happens is this is used for calibrating transducers that are used in clinical application. Okay. So PZT is more efficient in converting. So this conversion efficiency is important, and therefore PZT is kind of popularly used. So some of the key terms when you talk about transducer that you will encounter is this resonant frequency. What is this resonant frequency? Or if you excite, you have the best frequency, right? Your frequency response will be high at certain frequency. What is that? That is your resonant frequency, which is C by 2D. D is the thickness. So now you kind of see we said thicker the crystal, smaller is the frequency. So this is a connecting relation. F is equal to C by 2D. Of course, this has to do with the mode of propagation, the crystal, the stress strain of this crystal, all that we are not really going in depth. Okay. So we have engineered this crystal predominantly to do only this vibration in one mode, which is your thickness mode, and therefore your resonant frequency can be specified by changing the thickness of the crystal. So practical systems you get in this range of 1 to 20 megahertz. Of course, you really do not just introduce this. We will usually damp it so that you have about 3 to 5 cycles that go in. Okay. So this is the pressure wave that is introduced into the body. So what is our objective? Our objective is to create this plane waves that we talked about, right? You want, so when you have this dimension, so thickness is one dimension. What is the other dimension? The size, right? So thickness is one dimension. The other dimension is your, say for example, if thickness, if you call it in z direction, because that's how we have been using, then your xy is the other dimension. So when diameter d, right, of the surface is much larger than your d, that is your surface area is more than your thickness, right, longitudinal waves are transmitted into the body. So these are kind of engineering the crystal so that you predominantly get a compressional wave that can be sent into the body. This wave has to be sent into the body. So the condition in which, so you can cut this crystal, thickness is one direction, the other dimensions you can cut it to a disc or a rectangle. It can be a circular or a rectangular, right. You can have either a flat surface or concave surfaces. We'll talk about that as we go along. So essentially what you have is, you apply electrodes, right, you applied electric, you get displacements. So this is very routinely used, this piezoelectric effect is routinely used in different fields, right, in different applications, but we will consider it from our frequency range that is of interest here, which is going to be in megahertz. So we will just appreciate that this is a good crystal, that this crystal is providing us with the ability to generate the compressional wave of a desirable frequency, and also has the ability to detect this compressional wave and convert it to electrical signal with a reasonable efficiency, right. The conversion loss from one form to other is still not too much that it makes it useless. Okay. So we will do that. Okay, crystal was there. There is one another that was there in front, just outside the crystal. We saw what is called as matching layer. So here we kind of talked about this little bit. So the crystal is going to generate the wave, right? How do I send it into the body? Remember we talked about when you have to send it into the body, if there is air here, we talked about impedance mismatch. So first thing is the crystal can generate, but what is generated has to come out, right. So what you have is called as a matching layer. What does it match? Remember, impedance. So it has to match the impedance. So this matching helps in efficient transfer of sound waves from the transducer into the tissue, that is when you transmit. It is also true the other way, right. When the sound is getting reflected from inside the organs and it comes back, it has to leave the skin. If air is there, it won't leave the skin, it will go back in, right. So you need this matching layer to reduce the impedance mismatch. Okay. So your PZT, so Z here is your impedance, right, not the zirconium Z that you have here. So Z is about 15 times of Z of skin. So naturally, placing the crystal directly over skin would result in large reflection. Okay. So we will not, so you need a matching layer for that. In fact, after having the matching layer also, we talked about putting a gel and then placing it. Okay. So that is to really make sure that you are matched and you have sent out the trace of air that may come between the matching layer surface and the skin surface. You do not want air to come in that layer. Okay. So we put gel on top of this matching layer. Okay. So you have your transducer, this is your tissue, and so you need to have, in between them you need to have some matching, okay, so that it goes efficiently into the tissue, otherwise everything will come back. Okay. So this matching layer is usually a quarter wavelength, and of course we talked about this distance, right, thickness related to frequency. So clearly this matching layer also, when you say quarter wavelength, that means if you have one frequency, you have one wavelength. So it is probably efficient only for that particular frequency. In reality, you will know we have wide bandwidth signals. So you may have multiple layers. Okay. So when you have multiple layers, they engineer the Z effective, right. You have multiple layers, matching layers. So you kind of match it, and they have some design constraints. So you can get your effective to be square root of what is your tissue impedance and layer. Okay. So again, these are engineering the matching layer, which we will go little light. We will assume that okay, there is a material science, you have to adjust the impedances, and so materials manufacturing, that it has a lot of role in this part of the instrumentation. Okay, so then we talked about converting. So how there were electrodes, if you see, right? There was a crystal, you had matching layer, and then there were electrodes. So electrical signals of interest, right? How do you excite it? So you can do two ways. You can get continuous wave or pulse echo. Two operations are possible, meaning you can continuously excite. So if you apply a V which is continuous, right? V naught cos omega t. So you are applying it at a frequency that is the resonant frequency of the crystal. So you know the thickness, so you know the resonant frequency. So the efficient conversion happens when you apply a frequency that is at a resonant frequency. So if I apply V as V naught cos omega t, then the pressure wave will also be continuous. That is one way of operating. But predominantly all of the imaging scanners that you will see actually work based on pulsed ultrasound. Okay, what is pulsed ultrasound? I just apply a cosine, right? That we already saw. We apply a particular frequency of few cycles. A pulse signal is introduced, allowing to separate reflected signal from targets. So the idea here is this: instead of continuously applying, I will send a short burst, right? I will apply a sinusoid for a short duration. So that's why we call it as pulse. A small, right, 2-3 cycles of a sinusoid I will hit. Then what happens? This pulse goes inside the tissue. It gets bounced back, as we saw, right? Reflection, refraction, and then your scattering, all that happens. So some amount comes back. When it comes back, it is hitting your crystal, right? Matching layer and then your crystal. So when that happens, that is converted to your electrical signal. So you apply a pulse and then the pulse goes into the medium, it comes back. So based on when you sent the pulse and when you receive the pulse, right, when and how much you receive the pulse, you can comment about where the boundary is. Because I know the velocity, right? If I assume my velocity in the medium, I know when I am sending it, when I am receiving it. So if I know the time and I know the velocity, I can locate my distance, right? So essentially time of flight calculations can be done. So pulsed ultrasound, pulse echo. So you send a pulse, receive the echo of that pulse. This is the most predominant usage for ultrasound imaging, pulse echo scanning. Okay. So going forward, we will focus more on the pulsed ultrasound. We will just leave continuous wave as is. I mean, some of the typical applications that you will see, that we saw Doppler, for example, right? So you do this if you have gone for a if you have gone or had a chance to go with somebody else, you would have when they are pregnant, when they go for a checkup, right? They will have a instrument which is an ultrasound instrument. They move it around the tummy, and suddenly the fetal, right, if it is pumping, so you could start to hear. So essentially what happens is, it is a continuous wave. They move around, and because of the Doppler principle, you hear a shifted Doppler frequency. It turns out that the Doppler shift is in the audible range, and therefore they use that. So continuous wave is useful, but predominantly for imaging purpose we use pulsed mode. Okay. So when we talk about transmit pulse, this is a typical transmit pulse shape that you have. So 5 megahertz transducer pulse. So this is what is created. This waveform, this pulse is what is sent into the body. Okay. So a short burst, a few microseconds length here, right? So this is what is sent into the body, and then you start to listen to the echoes, and the problem proposition is simple. Based on the echoes, how much I am getting, can I say where is that interface, where is that scatterer? Okay. So in some sense it's very simple. I send a pulse in, I get a echo back. Based on the echo and this information of when I sent it and how much and where how much and after how long I am receiving the echo, I have to say where is that R, where is that reflectivity, that scatter, right, where is that, or the interface, where is that, okay. So that is your transmit pulse. An important aspect here, like I keep saying, we'll kind of recognize it here as well, because we talked about this pulse. Remember, we already talked about this lambda, and I said it is related to the resolution. So in here, what is your resolution? Resolution is the ability to resolve two things. In our case, what is this two? Oh, spatially separated interfaces, right. So I have two interfaces. Can I separate using this pulse the two interfaces as being two different, separated by a distance, right. What is the minimum distance that you should have, so that this pulse, I can tease out from the pulse that the echo 1 is from interface 1, echo 2 is from interface 2, okay. So clearly you have this pulse, it is getting reflected, right. This is echo 1, it is getting reflected, this is your echo 2. Of course, echo 1 and echo 2 are separated in time because the interfaces are separated in distance, right. So if you do that, you are receiving this echo. So now your objective is, from this received echo waveform, which you get continuously with the time, right, you have to say whether these two are coming from two different interfaces. So clearly you can see that this ability to resolve these two interfaces depends on the length of this echo, the length of this pulse that you are sending, right. So pulse length, your axial resolution in ultrasound, axial or the direction along the depth, right, your compressional wave, so the wave propagation direction, that is called as axial. So pulse length directly is dependent on your resolution, is directly dependent on your pulse length, which you can, at the limit, you can think about sending a pulse only one cycle, so your lambda. So typically it is q lambda by 4. Q, essentially you can consider that as a quality factor that determines your shape, right, that incorporates your shape, okay. So now you see vividly that when you use pulse ultrasound, pulse echo paradigm, this wavelength is a big deal, that determines your resolution, axial resolution, okay. So let's move on. So now what we want to do is, in a simplistic term, what we said is, okay, I have my transducer can create a plane wave, and even more specifically we said we will create a pulse and send it into the body. Next the question is, oh, I already know what happens if a pressure wave, right, the plane wave that we already talked about, goes into the body. It goes through reflection, refraction, scattering, okay. So now the question is there anything more that we need to understand, because we are creating these pressure waves, right, we are creating using this transducer, right. Is there any detail? Can I get my plane waves to be exactly, along the plane, right, along the plane wave front, every location we had the same pressure, right, that's why we called this plane wave front. Is it really true, right, is it really true? Meaning, when I create this, is the pressure changing at the center as you move along the side, right, you have 0, 0. Is the same pressure there at the lateral edge, in the other lateral edge, right, is it same, is it truly a plane, right. So it turns out that it's not as simple. So we call it as beam pattern, because you will realize that it is not a straightforward visualization. So what happens is, when you use this transducer, right, when you try to operate it in the compressional, the thickness mode, right, when it is trying to do this, it turns out that the wave that is coming out is actually inherently diverging in nature. So it is not just going to be restricted to only the very in some sense very similar. We talked about X-ray tube. Inherently it comes as a cone shaped, right? So here also, if you notice, even though we have engineered the transducer so that it is predominantly doing this, the moment it comes outside the transducer, inherent nature is for it to diverge. Okay. So now the question is, that means the pressure wave, when it is diverging, the intensity is going to be different whether you are situated along the center or you are moving away from the center. Of course, the pressure is also going to change with the distance, that we kind of saw P of z, right? That is how we wrote P of z comma t, but that part is fine. But in the other direction, right, in the xy, right, when it is going, so the z direction we already saw, it is changing, pressure is changing with the distance, but even that is not straightforward, as we will see. So essentially what we have is, we need to understand. So the objective is this: I am sending the sound wave, I get an echo. Based on the echo, I have to say, right, what interface is there at which location. So based on the amount of echo is proportional to your impedance mismatch, right? So based on the amount of echo, can I say that it at this location this is the impedance mismatch, or more specifically, this is a impedance mismatch occurs at such a location. So clearly, if I want only along z, right, that is one thing, but we are interested in imaging, right? So not only we should be able to locate in depth, we should also be able to locate in the azimuthal. Then only we get an image, right? If you look at the image, typically you have a depth direction, so skin will be at the top, you have a depth, and then you have the lateral width. So if I pay attention, what we have done is P of z comma t. Z is only depth direction, but I want to do imaging. So I want to not only say that, oh, there is a obstruction, there is a object situated at 5 centimeters from the skin. That alone is not sufficient. I should be able to say, oh, it is situated 5 centimeters from skin and 4 millimeters to the left of the center. I should be able to say that, right? In that context, the transducer is generating the pressure wave, but then it is generating this 3-dimensional wave, right? It has a and it is also spreading. So now the question is, how do I describe this beam pattern? How do I capture this beam pattern? Because once I can capture what pressure is going, what is the pressure distribution, then I know what I am going to get. What I am going to get is this pressure into the reflectivity, right? That is what I am going to get back, your R, reflection coefficient. Incident times the reflection coefficient is what you are going to get. So what is incident, right? It is not one. So the incident could be a change, it could change over the area, it could change over the volume. So we need to be describing that. So in order to do that, at the first level, roughly this is what you see. There is a geometric region. So depends on, so there are key terms that we will encounter. So what we will have, what is called as a near field or Fresnel region. So essentially what it is you have your thickness mode, right, of your crystal. It is sending out pressure wave, it is doing this, but then after some distance it starts to spread out, widen, right. So the region over which it is still holding on, right, is your geometric region, which is your and then you have what is called as a near field, near to the transducer. You can clearly see, the idea is the farther you go from the transducer, more diverging it becomes. So how much, so some context of whether you are near to the transducer or far away from the transducer is having an effect on the pressure field that each location is going to experience. So you can see here there is a lot of fluctuations. So in the near field you can see there is a lot of fluctuation, but it is not wider than your transducer width, whereas when you go far field, far away from the transducer, you see the intensity is smoother, right? It more near the center. As you go away from the center, the intensity of the pressure is reducing, right? But it is wider. It becomes wider region. Okay, so there are the behavior of the beam is different, whether it is close to the transducer or which is near field, Fresnel region, or Fraunhofer region or far field. So also it depends on the type, the shape of the crystal. The thickness controls the frequency, the shape controls your beam pattern. So if it's a circular transducer, it turns out that you can retain this geometry, right? You can, geometric region can maintain as d square by 4 lambda. So it can retain before the divergence kicks in, before the width is greater than your d, right? This is the length over which z is your this direction, right? Z is this direction. So depth over which you can have this divergence less than your d, your aperture size or your crystal dimension, right? That is your a square by lambda, I mean d square by 4 lambda. This is radius, so ignore. D is the diameter. So d square by 4 lambda. So if it is going to be rectangular geometry, then you can have, so rectangular transducer, you can have d square by 2 lambda. So the textbook goes on to deal with rectangular transducer, right? What we will do is we will now kind of orient ourselves, relate back to the textbook chapter on imaging. So the chapter on instrumentation, we started with the instrumentation, but then this is probably a point where we understood the transducer is going to create this wave, but when you create this ultrasound wave, when it comes out, it is not going to be nice, well behaved, just wave which is going in one, only along the depth. It is going to spread out. So now we will talk about how it spreads out and what happens to the wave when you use this transducer. Then we will come back to, okay, now I understand the wave, how it diverges. So what happens if that hits my scatterer, so my object that is a distribution of reflectivity, what is the echo I am getting, and therefore our imaging equation and image reconstruction, that part we will get. Okay. So we will stop here with the beam pattern. We will continue further. We have what is called as width, right? This is, so you have one direction along z, which is your direction of depth. We talked about axial resolution. So what is the importance, or why is it important to understand this beam that is spreading out, or the beam width in the other direction? Because we are interested in imaging, right? We want to do imaging. That means along the depth you will be able to separate two interfaces, as we saw using the axial resolution capability. But then what about two objects that are in the lateral direction, right, along the width? How do you separate? Oh, now you see that there is to be, the idea is this is spreading out. If this is spreading out, then there is going to be a challenge in saying, right, the lateral direction, how two objects can come close together. So the idea of axial resolution is related to the pulse length, but the idea of lateral resolution is going to be dictated by your beam width. Okay. So lateral resolution is roughly equal to your beam width, which is in the near field, like we saw before it starts to diverge, your dimension d is there. So okay, so when you have a transducer and you want to do an imaging, you are going to, this is only one direction, depth direction. So I should be able to move it in the other direction, right? Only then I can get an image. Okay. So x comma z, I can get my image plane as x comma z, for example, based on the x that is written here, right? So if this is the case, then I need to I need to have as narrow a beam as possible, right? Only then when I move in x direction I can have good resolution. So the idea about this beam width, right? So you have pressure, this is in the lateral direction, x direction. So if I have two transducers, notice here the right one is able to resolve better because its beam width, beam spread is less. So beam width is an important parameter. So when you come close together, this starts to blend in. Here you completely lose in the lateral direction, right? Whereas in transducer A, right, some example A, which has less spread, the beam width is less, right? So here, right, this is what we are plotting. So beam width, when it is a narrow beam, right, then the ability to separate in the lateral direction becomes better. So your lateral resolution is better. So clearly you can see that the dimension of your aperture, D is what? D is your transducer aperture. So your dimension of your aperture plays a role in the lateral resolution. In the axial resolution, it is the pulse length. Okay. So therefore it becomes very important to understand about this beam width. So beam pattern, we want to understand how we can shape the beam so that it can have as narrow a beam width as possible. Okay, that is going to be your beam pattern. Just a overview slide. So ideally speaking, we said, oh, you will have the spread, but in reality, if you have a view, this is all the pressure intensity experience at different locations. So this is your depth direction, this is your x direction, if you will, right? Notice the pressure distribution, nothing close to what you would straightforward imagine, right? We would have imagined plane wave front. So everything in the plane is same, and therefore if this is my z direction, all the locations will experience same pressure. That's not the case. If you are near field, you get some weird intensities, right, where you are experiencing. So this is why it is called as beam pattern. So there is a pattern to it, in the sense that close there is a lot more fluctuation, whereas when you move away you get lot more smoother, right. So the idea is we need to spend a little more. So depending on this beam pattern, whether I send the pressure wave, when I send the pressure wave, this is how it is going to insonify the region. So what I am going to get echo back is based on what is hitting at that location, what the impedance mismatches, right, that is what I am going to get back. So it is important that we understand what are the different beam patterns, how do we define this beam pattern, how do we get a handle on this beam pattern. If you get a handle on this beam pattern, if I can tell the pressure distribution, how it is in space of the transmit pressure that you are sending, then we should be able to get an idea on the, based on the receive signal, I should be able to map out where the scatterers are located, type and location of the scatterer. Okay. So we will stop here, we will talk about the idea of diffraction in the next episode. Thank you.